Welcome to Pythonic, and today I will show you how to rescale data with very high range, where you need to see high and low end values. So first of all I will create sigmoid function which is reduced from 1 to 0, and I will adjust the weight of this function to 5, and I will multiply it by 1 million to make it very big and add 1 to make it small positive at the very big values of x. So then my function will be just random 5 cosine x multiplied by sine from x plus pi over 4 and multiplied by sigmoid function. And I will take out 3 to make it kind of symmetrical. Then I will create data, so it will be line space from -10 to 10 with 1000 steps. And let's calculate this function and check minimal and maximum value, so it's almost symmetrical from -732,000 up to 4 million. But I would like to see how it behaves at low values as well. So let's plot it. So first of all, let's plot original function. Just plot it as a graph and do not do anything. So let's see what happens. So I will do multi-plot draw. So you can see at the beginning how it's behaved, but I cannot see its behavior at x bigger than 2. So we need to resolve it somehow. So let's do something. So first of all, we can reduce the limits and show only low values and say that at the high value it's not very important, as we can see from this graph. And okay, we can see the oscillation on the x higher than 2.5, but we cannot see anything what was happen at the low x's. So that's why sometimes it's not very good. It's only good when you know that there is nothing interesting in the series happen. So second idea is to take logarithm. But the logarithm from negative value is impossible to take, and you need to split your data for positive and negative set. So let's create NumPy array for storage of the data, and then create positive mask and negative mask for positive and negative value of y. So to calculate logarithm for positive value, we just take logarithm from the positive values, and to calculate logarithm from negative values, we change them to positive by adding minus sign, and then we change sign of the result again by adding minus sign again. And as you can see, we've got some peaks around 0, which is because logarithm around 0 is almost infinity. To avoid this, we can use logarithm plus 1, which calculates the logarithm from the value of x plus 1, and this avoid very big jumps around 0. So now let's do plus 1 logarithm. So we do everything is the same, but using NumPy function log1p. And let's see, as you can see, we have no problem around very low values and around 0, but it's scaled differently because it's natural logarithm. But you can rescale it to logarithm with a base 10. So and now let's introduce pseudo-logarithm. Pseudo-logarithm, it's some kind of logarithm which is logarithm at the big parameters of x, and between small parameters it's kind of linear. So hyperbolic arc sine divided by logarithm of 10 will give this function. So let's apply it, and as you can see, the hyperbolic arc sine is defined on all range, and you don't need to split it on positive and negative values. So let's see what's happened. By the way, the description of all this function you can read in the blog with the links under the video. So let's do some minor changes, and now let's see the result. So as you can see, this pseudo-logarithm graph looks like a normal logarithm at the high values of y, and it's almost look like function itself with low values, which is quite good for further analysis. What else we can do? Another prominent way of scaling is to take a root of high power, for example, root of power 10, or just enter everything in the power 1 over 10. And again, we need to split in positive and negative mask. So let's have a look what's happened. So you just multiply, do power of 1 over the 10th. The root with odd values like root of power 3 or root of power 5 or root of power 9, you do not need to split to positive and negative mask, but Python unfortunately cannot manage to work with this. So it is quite good, and you resolve the low range much better than for logarithm. but the values are not very obvious, and it's only good for, and this root scaling is good for qualitative analysis, but not for quantitative analysis. And last one, you can use combined graph where you do some combination of different scaling. For example, for big values, y over the bigger than 5 or smaller than 5, you use logarithm, and for small values, you just plot y by itself. Let's see what's happened. So let's do for big values, we will use logarithm, and for small values, we will use just straight value. For big values, we use pseudo-logarithm. So let's see what's happened. And it looks good again, but on the position of the jump between two graphs, you've got some peaks, and some peaks are hidden. So it is another good way to represent the data. And now let's see on real data. So I will use 2D data of some oscillation with very strong source and very weak waves around. On the original data, you cannot see any information behind the source. But with limits, you can see how the waves are distributed, but it's very difficult to estimate what's happened with the source. And logarithms show much better data, and pseudo-logarithm show quite nice data, and root scaling show very sharp scaling. So now it's up to you which way of scaling to choose, but as you can see, all of them can give you some good results, and you need to check what's better work on your real data. That's it for now. If you like this video, please subscribe to my channel and wait for new interesting video. Thank you. Bye.